Eric probably doesn't need an introduction to this crowd. You all know who he is. Just very briefly, you know, his PhD was in 1995 from the University of Washington. He went away and then he went back to the University of Washington where he is now. He has been the director of the Quaternary Research Center. He's been the senior editor of the journal Quaternary Research. His you know, Google Scholar citation H index is very high. It's a little bit enviable. He's published in the journals that you've all heard of many, many times. He's led some of the major ice core drilling efforts in Antarctica. And he's also the co-founder of the Real Climate blog that many of you probably follow. I first knew Eric when I was an undergraduate student. I didn't know much about anything in those days, but Eric was there. And then really it turned out that what Eric did in his career after that benefited me mostly because he ended up as a stint at Instar as a postdoc, and he helped my predecessor who worked with Giff Miller, Mike Kaplan, set up a cosmogenic isotope lab, a beryllium lab. And that was really to my benefit because I came into Instar a little bit after that, and there was a lab basically set up ready for me to do all my work. So I have you to thank for my dissertation. So anyway, without further ado, yeah.
Thanks. I'm going to turn on the microphone here. Is that working? No. Is that working? No. On. How's that?
Yeah.
Great. So, as long as we're telling stories about each other, I'll tell you a story that I don't think you've ever heard, which is that, so when Jason applied to work at Instar with Giff Miller, I wrote him a really good letter. I don't think I have a copy of this letter. But I know it was really good because Giff called me and said, "Is this for real?" And I remember thinking, well, I think Jason's really good, but now my reputation is riding. Like if I say yes and it works out poorly, Giff will never forgive me. But I think he's forgiven me.
Well done.
Thank you. So, I heard a few people say, talk about what you're working on at the Arctic Workshop, which is good because this is very much work in progress. I'm going to show you some stuff that's published, but it's really preliminary in a lot of ways. Part of me wants to talk about stuff I'm doing in Antarctica because my main focus has been Antarctica for most of my career, with little bits of work up in the Arctic. I am sort of returning to Greenland, or at least I'm sending students there with this project that Jason is leading. So I'm going to mostly focus on the Arctic, but I'm not going to talk about data I've produced particularly. I'm going to talk about this methodology that I'm getting involved in using and sort of try to advertise it to you and tell you a little bit about what it's about and why you should be interested in it. And I might tell you a bit about the potential pitfalls, but since this is an evening talk, I'll probably make it sound better than it really is. Well, this is slightly cut off, but that's sort of okay. Students. So I want to start by acknowledging Greg Haycom, who is he's a weather forecast guy. He's the chair of the Atmospheric Sciences Department at the University of Washington. And this collaboration began basically because through conversations with me and David Battisti at the University of Washington, Greg became interested in the idea that he could apply his skills with weather forecasting, which is all about data assimilation, to the paleoclimate problem. And so we've been doing this together for a few years now, and we have a project funded together called the Last Millennium Reanalysis Project, NOAA funded, and there's several other PIs. I'll show you their names in a bit. Much of the work I'm going to show you, especially towards, well, really throughout the talk, is due to Greg's former student, Nathan Steiger, who I co-advised, and Jessica Badgley is a new student of mine who's going to be going to Greenland with Jason this summer, who's also started to work on this and some of her preliminary results I'll show towards the end. Nathan is now at Lamont, Georgia. And I think he's a real leader in this field and really worth talking to if you're interested in it. So Arctic temperature change, 79 to 2012, just from a nice figure that I found in Nature, which was a commentary on a paper by a colleague of mine, Xinhua Ding, from 2014. The point of this figure is to simply say, it's all about the spatial pattern of climate. It's all about the spatial complexity of climate. Everything we do in trying to understand how climate is changing, how it will change, how it has changed in the past, you can't really ultimately just rely on like global averages. You've got to have fingerprints about how the change is happening in particular areas to understand the dynamics involved. And this is it. I keep walking back because I forget I've got this thing. This is illustrated in a paper that you may have seen recently by Xinhua also. He was a postdoc of mine for a few years. He's now at Santa Barbara. We just published this paper like last week, and people are mad at us because what the paper says is as much as 50% of the sea ice decline is natural variability. And people do not like this. But maybe it's wrong, but I think that's what the results say. Never mind the controversy. The way that we get this result is through the spatial pattern of climate. And in particular, this just shows that same figure I just showed you, but from our paper, the trend in temperature, and associated with the trend in geopotential height. I think this is 700 millibar height change. So that's the observations, and this is a climate simulation. And basically the point is it's about the pattern and the correspondence of the pattern, in this case, between the atmospheric circulation change, which you learn about from looking at the height changes, and the pattern of temperature change. You can ask me about this particular paper if you want to later, or argue with me about it, whatever. The point is that when we look at modern climate data like that, we're looking at spatial patterns and, of course, temporal change. And we're using these reanalysis products mostly. I once joked to David Battisti when he said something about how many more papers people in his department, atmospheric sciences, publish than in my department, Earth and Space Sciences. I blurted out, that's because you don't do anything except download reanalysis data and publish it in Nature. We have to produce data. But there's a real disconnect here, right, between this incredible hourly resolved climate data that you get from those sort of products covering the whole globe. These guys refer to those reanalysis products as observations. We tend to talk about models a little bit more. We've been trying for a very long time, right, in the paleoclimate community to take the spatially sparse but temporally long records we get from paleoclimate proxies and make global pictures out of them, right? So this is just an example from our good friend John Snowberpack, formerly of INSTAR, from this paper that they wrote in Science in '97, which was a compilation of Arctic proxy data used to infer the pattern of pattern and the magnitude of Arctic climate change over the last 400 years. And what they did in this particular case is very qualitative. There's proxies that are believed to be or shown to be sensitive to temperature, and they put them all together and they standardized them, and they said, it's about whether it's higher or lower. And they were careful to say that we don't know exactly the quantitative translation here. We're not going to claim that we did right. Around the same time, of course, Mike Mann was working on his now famous / infamous hockey stick work, and that was really an attempt, not just an attempt. It was one of the first major compilation of taking paleoclimate data and putting it into this global context in a quantitative statistical way. And whatever arguments one may or may not have with Mike, the reason he's so famous is that this, especially for those of us who produce these paleoclimate records, this was a huge breakthrough for me and others mentally. It's like, oh, this is how we put all this stuff together into one framework. And I would argue it created an entirely new field, in a sense, of doing this sort of thing. And yet, we're still in many ways reliant on qualitative interpretations. So the Pages 2K proxy data compilation published in 2013, again, did kind of what Overpeck did. This is not a quantitative picture. Well, it is quantitative, but it's not been translated into temperature. It's sort of standardized. Is it warmer or is it colder? There are, of course, many reconstructions like this that are done quantitatively in the sense that translations are made from the proxy data into temperature in this case. Other climate variables can be done, of course, but mostly as temperature. So this is just another example from Raphael Newcomb, 2014, using lots of proxy data and looking at the temporal variability of hemisphere average temperature, northern versus southern hemisphere. And I show this figure partly to sort of remind myself to mention that a thing we like to do then is compare our quantitative or qualitative reconstructions with model simulations, as is done here. Wouldn't it be nice to not have to do it that way, not to have the models over here, the simulations over here, and the data over here? Going back to my colleagues in atmospheric sciences, that's not what they're doing. These things are blended together. They're two different versions of reality. One is data, observations in some locations, and another is more or less data as well, but it's informed by simulations. It's informed by climate models. That's what the data assimilation idea is all about, speaking qualitatively. I want to just say one more sort of negative thing about what most of us have been doing for most of our careers, at least in the proxy, time series production world. We almost always rely on calibration. That is, we take, this is again from the Newcomb paper, and down here is showing, evidence that the calibration and the verification against the instrumental temperature record is good. And as I'm sure most of you are aware, these kind of exercises are limiting because you can never really be totally sure that no matter that it's stationary, right? You do this and you say, well, I exclude half of the data and I see whether my statistics hold up. And then they assume that that applies in the past. And there's a lot of good evidence that it doesn't, right? Different records of El Nino, just to take one example, that are demonstrably good by these sorts of measures diverge from each other before calibration verification window. So it's like, you kind of know they're all wrong, or maybe one of them's right, but you don't know which one. Okay? Now, we're not going to entirely solve this problem with the methodology that we're working on, but I think we are making significant progress to doing it better. So there's been a really rapid growth in the use of these sorts of techniques. We'll get into what these techniques are in a minute, but Greg Haycomb has been one of the leaders of this. This is from the Pages newsletter in 2013. I just did a Google search this morning on paleoclimate data assimilation, and I actually got 8,000 hits. Sort of surprised me. As I went through them, I realized, okay, some of them aren't actually about that. But nevertheless, it was several pages. There's quite a few publications. Greg shows up a few times. Hughes Goose in the Netherlands shows up a lot. And some other names that I don't know as well, but just other people are doing this. So I want to talk about basically what we're doing, why we think it's powerful, why we kind of think it might be the right approach, and show you some results. So just briefly, what is paleoclimate data assimilation? So data assimilation in general is a way, it's the optimal way, probably, to blend short but spatially complete data with long but sparse data. That's the paleoclimate reconstruction problem. And in the language of this literature, we're talking about combining a prior, that is your first guess in a sense, your initial guess about, for example, the spatial temperature pattern in the globe, with observations, for example, known temperature data at given locations. So this is what weather forecast people do, right? They have an initial guess, which is their last forecast, and then they have the data at the time that goes into their forecast for the next hour or whatever. right here I wrote, unlike purely statistical methods, well, this is purely statistical, but unlike things like Michael Mann's early work and later work as well, which rely on things like taking the temperature field of the globe, which has many degrees of freedom, and trying to get rid of the noise and be left with a few degrees of freedom by EF kind of analyses. The trouble with, why is that bug happening? The trouble with, the potential problems with this sort of analysis is that you can throw out information, which isn't actually noise, it's information that you want. And this is just linear mathematics. It doesn't necessarily result in climate reconstructions that are physically realistic, that are consistent with the dynamics of the system. The idea here is to use climate models which are driven by the physics as we know it, and within certain parameters are realistic, are dynamically realistic. An additional thing, which I'm not going to talk about much, is that there's this sort of subfield that is referred to as proxy system modeling, which tries to circumvent the problem that you have to calibrate. And just in essence, the idea ultimately, the sort of holy grail here, is to incorporate all these things about how trees grow, how oxygen 18 fractionates in the atmosphere, et cetera, into the climate models, so that we can compare simulations of trees with trees, rather than temperature from a model compared to temperature inferred from trees. So it works a little bit backwards conceptually in the other direction from much of what we've done for many years. Okay, so just a little bit of a side. Here's me about, I don't know, it's actually a couple years ago, but this event occurred maybe 3-4 years ago. I was at NASA GIST and I asked Gavin Schmidt, what do you think of this idea that I'm embarking on with my buddy Greg of using data assimilation, paleoclimate? And that's what Gavin said. So that's it, go have dinner. This was my initial reaction. Gavin's a very smart fellow, and he's one of the people, the very few people whose background is in physics and climate modeling, who has really embraced the paleoclimate community and has really learned about what we do and has spent serious time thinking about what we do and sometimes doing it himself. You know, he was the first person to create a global compilation of oxygen 18 in the ocean. I mean, it was a huge amount of work just compiling data, right? This is something a lot of modelers don't do. I have a lot of respect for him, and I was rather, well, I felt like that when he said this. But he's possibly wrong, and he might have admitted this to me at a workshop recently that we had on this subject. And I'll touch a little bit on why I think why he said that and why that wasn't a relevant comment. So, little cartoon here from a paper we published last year about what this is about. This is from Julien Mioget, who's a co-PI on this project with us. So the essential idea is, so you have a climate model or some other initial guess. It might come from reanalysis climate data. It might come from a climate model. It might come from something you made up or from someone else's statistical result, whatever. It's a picture of the climate state for a given time period. Then you have a model of the proxy you are measuring, and you combine that model with the observations that you make, and you use all of this information, and you run it through what's called an ensemble Kalman filter, which is the way that most weather forecasts work. And I won't go into that other than to say it's actually simple matrix algebra, but there's a lot of nuances about how you create and calculate these matrices. So there's some math there, and then you go back and you update the climate model and you go around in a circle like that. So again, this thing here is the prior. It's your initial guess. The proxy system models translate the prior. Oh, yeah, this is actually an important distinction. note where this sits. We're not taking these things, the observations, and converting them to temperature and then comparing with the model. We're actually taking the model output, which might be temperature, converting it to the proxy, and then comparing the proxies. There again is the math. Now, here's where Gavin didn't quite understand what we're doing. In weather forecasting, after you do that math, you go back and you update the model, and you really do go around in a circle. Now, we actually are trying to do this now, but the results I'm going to show you don't do that. This is computationally very, very expensive. As soon as you put an X here, some people will tell you that you're not doing data assimilation. You're just doing math. All I can say is Greg Haycom has written books about data assimilation, and he thinks we're doing data assimilation because the math is the same as one uses in the weather forecast world. The reason that, you really want to do this, right? You want the model to know about the data. But the trouble with this is that that's only useful if there's predictability in the system on the time scale of the proxy observations. If the observations are like 500-year averages of sea surface temperature, there is no predictability about the next 500 years from that. The best we do typically is annually resolved, and there's very little predictability in the climate system on that time scale, except in the tropics, where actually doing this makes a difference. High latitudes, not so much. So it would be nice to do this, but it's actually not clear that it's worth your time. And as soon as you realize that, you can do these calculations on a laptop instead of a supercomputer. It doesn't mean that we don't sort of use a lot of information here. It simply means that instead of forward stepping the climate model, we just sample it multiple times. In fact, we can sample multiple different climate models. So instead of getting an ensemble of results that sort of evolves in time, we get an ensemble of results that has different priors. And from that, we build up statistics about how good our final result is, how sensitive is it to our initial guess. And in the ideal case, the data are strong enough constraints that the initial guess doesn't matter very much. Last point I want to make about this is that this whole methodology is all about keeping track of the uncertainties. So the weighting that you give to the observations versus the model depends on a lot of details here, like what you put in basically for this matrix R right here, which is the data covariance. So I don't want to go into too much detail, but just a little bit more. This part right here is the critical thing. It's the critical sort of engine, or the gasoline that goes into that engine, which is comparing observations and your model or your prior result. So an example of this, again, is temperature derived from tree rings versus temperature from a climate model, or tree rings actually derived from temperature, and from a climate model and just tree ring width. Okay? You could also do this sort of thing, temperature derived from an ice core, oxygen 18 measurement, versus temperature from a climate model. But what we really want to do, and we can do it now for oxygen 18, our observations in our model can be of the same data type, and we're not changing the proxy at all. We're just taking the proxy data itself, and we're taking the simulation from a climate model. Okay? And O18 in climate models works very, very well now. There's been huge advances in climate modeling. And the isotopes, which are actually fairly simple and the physics are well understood, have improved with the improvement in the climate modeling and the fidelity of the climate models to simulate the real world. Okay, so now a few results from our very first cut from this last millennium reanalysis project. Again, it's funded by NOAA. We also got some P2C2 data funding to get us started. And we're basically saying, let's test this methodology with the same data sets. Initially, we used the Pages 2K data set that other people have used to sort of compare results and look at whether we get improvements. We're still relying on simple calibrations for now in this work. And here's a list of the co-PIs on that project. So this shows the results of our calculations with the Pages 2K data set for the last 120 years. In black, global average global mean temperature compared with all these other compilations, GIST, TAMPAD, CRU, et cetera, Berkeley Earth of global mean temperature. The comparison is very good, right? What this shows is that, so the black line contains climate model simulations and proxy data. And all of the temporal variability, the fact that it gets a bit warmer here and cools down and gets warm again, all of that comes from the proxy data, not from the climate model. We actually tested this with a control run of last glacial maximum climate, and the result is the same. The proxy data push our prior around until it looks like the proxy data. So there really, as I'm sure you all appreciate, there really is information about the decadal variability of climate over the last century contained in the proxy data. Okay. This is not so different than what other people have done. It's a linear calibration of data, essentially, because we are relying on calibrating the data against the instrumental record in the first place. So it's a little bit circular. This compares our last 2,000-year results in black with 95% confidence in, it's actually not confidence, it's the range of results we get in gray with the mean of 17 under reconstructions. This is just saying, we put in the same data, but we use a different methodology, we get basically the same result. There's some interesting differences to explore, but it's cooling, there's a hockey stick-ish thing, and then there's a, the blade, the hockey stick. Unsurprising, because that's what the data look like. We can look at all sorts of statistics. I won't go into this much other than to just remind you that correlation is nice. It's good when it's red. It's even better when the coefficient of efficiency statistic is red and it isn't red everywhere. This penalizes you if your mean is off or your variance is off, which the correlation coefficient wouldn't do. It's especially blue over Western North America, and we actually know, since the publication of this paper, some more work has been done, and we know that this is because we're assuming the trees there reflect temperature, but actually they probably reflect precip. And if we include that, that goes red, which is nice. This shows the same statistics, but not for temperature, but for 500 millibar height. So one of the huge advantages of this methodology is because you're using the climate model, anything that the climate model is doing to give you temperature output, you've also sort of got access to. If you save those variables, and if they co-vary with temperature in a serious way, in a statistically significant way, you can also extract from your analysis results, what was the temperature field in 1826? If you believe that's a good result based on the statistics, you can then say, well, what else did the climate model do when it had that temperature result? Well, the 500 millibar heights looked like this. This is where the dynamical consistency comes in, which is very powerful. So here's an example from our paper. Tree rings have a very large anomaly, which reflects there was a volcanic eruption, which shows up in ice cores in 1808, both in the northern and southern hemisphere. And this shows our reconstruction of the temperature anomaly for that year, 1808, 1809, et cetera, and the associated geopotential height field, which develops in a year or two after the eruption, a very, very clear geopotential height pattern, which is Pacific North America pattern. It sort of has to do this because this is what the real world does in the atmosphere, and this is what the climate model does. It's one of the ways it behaves. But it does it in a year in which we actually know that this is what happened, because there's independent evidence from instrumental records and observations that there was this sort of weather pattern developing. So that's kind of cool. Another example, 1941 is a year that I really like because my former student Dave Schneider, who's now at NCAR, took all our ice cores from Antarctica, which I had at that point still sort of thought, oh, we have a bunch of noise here, what am I going to do with this? And he said, the highest O18 value in every single core is 1940 or 41. And he stacked them together and he thought about this and he looked at other data and he said, there's a massive Central Pacific El Nino event in 1941, which is barely talked about. It actually doesn't show up as significant in the Southern Oscillation Index. This is a compilation of the available actual data, temperature data from that year, which is quite sparse, and sea level pressure data from Dave's paper on this. So I just like this year. It's a really anomalous year in Antarctica. That El Nino actually lasted from 39 to 42, longest lived El Nino of the 20th century. You can see it in the ice cores. You can see it in southern hemisphere and northern hemisphere temperature averages. Actually, that's tropics, northern hemisphere and southern hemisphere. This is the result from the last millennium reanalysis. If you stick just the ice cores in and you run this thing, the ice cores in Greenland and Antarctica and the tropics are telling you something about what's going on. There's not so many ice cores out in this region, so this is just sort of random. But you see this nice, this is 500 millibar heights now, anomaly in the same direction, warming over West Antarctica. I love this, right, because we discovered this from ice cores, but if you just use tree rings, you get the same results qualitatively. It's warmer and there's this large anomaly. And actually, it's worth noting that you get the El Nino out of this, even if you don't include any tropical ice cores, because the only way to get huge anomalies in a climate model in this part of Antarctica is to have an El Nino event. It's not the only way, but it's a good way to do it. Tree rings only are similar, and then the next slide is just like when we throw all the proxy data in. This is our best estimate from corals, tree rings. I think there's some lake sediment bars in here as well. This is the Pages 2K data set. Puts through this Kalman filter ringer, adjusting climate model results basically, saying this is our best estimate of what that year looked like in whatever fields you want, with varying levels of significance depending on which field you're looking at. Okay, so that's the big global sort of thing. I'm an ice core guy. I really wanted to get serious about the 018 and ice cores and to not have to calibrate against temperature. I want to do things that are independent of assumptions about stationary calibrations, and that indeed are independent entirely of the instrumental observations, so that we can have a pure paleoclimate record that is quantitative and is homogeneous, that is the same amount of data and the same kind of data throughout the record. So we can actually ask things like, was 1941 anomalous with respect to the last 2,000 years? Was it warmer than today, et cetera, et cetera? With no kind of ambiguity about different types of data and methodologies at different times. So Nathan Steiger led this paper, which I sort of pushed him to do, and I think he did a great job. He said, okay, let's do this, but let's just use 018 and let's just use ice cores. We used, as our prior, two different climate models, the NCAR model, CAM5 atmospheric model, and ECM5, to produce 018 simulations, and we assimilated the 018. And this is just to repeat my point before, that DCMs do a good job, do a demonstrably good job of getting isotope fields. That's the network of ice cores that we used. Okay, so these are the same kind of statistics I just showed you. This is correlation. This is CE. If it's blue, it's bad. Oh God, we're in trouble. But there aren't many ice cores outside Greenland and Antarctica. The verification for Antarctica is terrible. However, I published multiple papers making the point that the data are terrible. We actually have better data about Antarctica from ice cores than we do from temperature compilations. Here we're using the Berkeley Earth temperature compilation, and I can show you how completely bad it is. So this doesn't worry me too much. Anyway, the Arctic workshop, we're going to talk about Greenland, which remains significant by both of these measures. I won't show this, but we also get pretty good statistics for the atmospheric circulation over Greenland as well. Okay, so zooming in, this map, where it's not dotted, we have statistically significant correlation coefficients. And so what this says is based on the locations of cores here, the actual data from cores, we should be able to reconstruct, we can reconstruct the statistical significance, all of Greenland, and the surrounding seas as well. This is the same thing, but the CE statistic showing the same pattern. So just a couple of examples from sort of randomly chosen times. This is our reconstruction results for the year 1989. And here, plotted in exactly the same colors, is the observations. This is not exactly observations, it's weather forecast result from the high-REM model from the Danish Meteorological Institute. It's the best estimate of the temperature field back to 79, driven by ERA interim reanalysis. Same color scale, so this is good. Our ice cores only say it was cold in Greenland, maybe a little bit of warming on the east side. Again, the temperature scale is the same, so that's pretty satisfying. Another random year, 2000, is just sort of an interesting year because it's colder than average over the northeast of Greenland, but it's warmer than average in the southwest, and that's the same result we get from this reanalysis. Now, I do want to say I have not taken the time to go through every year and plot these, but I did choose these arbitrarily. It's probably not as good as I make it look. I was like, this looks good, I'm going to stop here. But it at least it illustrates the potential, right? Because we don't have any data here from these areas. We only have data we're only using data from the ice sheet and from Svalbard. And the climate model is telling you, this is what I think it looks like in places you don't have data at times when you have a particular pattern. Again, that's what weather forecasting is all about. This shows a time series of Greenland mean temperature compared with the Berkeley Earth average, 1900 to 2000. The blue is our reconstruction. This is the coherence between the two versus period versus frequency. So the point here simply is we have significant coherence on time scales of sort of 5 years and lower, which is good, right? Like decadal, confident decadal reconstructions is a good thing. Okay, so now this is very preliminary. Jessica Badgley, my student, did this. I'm sure she did it right, but there's a lot of stuff we have to do to really be confident in our results. This is the last 200 years. The blue is her results, and here we're actually doing the traditional 018 calibration stuff first, because it's just easier. The black shows Nathan's work where he didn't do that, where he just assimilated 018. The results are very, very similar, which is great. This is all the available data that we have at the moment, annual result in blue. And this is from the 8 long records that exist, because we want to go back in time. Of course, with only 8 records that are lower resolution, we have less variance, but the red nicely looks like a smooth version of blue, so we seem to be getting good results. So this is what you get if you just take all of the available ice cores from Greenland and do this reconstruction using a prior, which in this case is actually the ERA interim data, but we've also done it with climate models, and it's not any different. I want to actually emphasize one really simple thing here. If I plotted the prior, it would be a flat line at 0. Okay, so all of that information about the temporal change and its variability comes from the 018, which is why it looks like the 018, right? So why, Eric, didn't you just average the 18 out for ice cores and leave? That'd probably give you the same result, but you wouldn't get this sort of information. We're instantaneously, in a sense, by doing this, getting a spatial field of temperature for the globe. Now, since the only data we've stuck in here is Greenland, all of the information out there is not constrained by data at all, but it is constrained by dynamics. And the dynamics say a good way to be warm in Greenland is to be cold in Europe because of the North Atlantic oscillation. So you see in this result where we haven't constrained outside Greenland, you see this all the time. This is kind of the dominant mode of variability that's in the dynamics of the system. It tends to be cold over Europe. So that's just, again, that's sort of a random year, 1995. Sort of fun to just choose a warm time when the average over Greenland is warm. Our result actually says it might have been cold in the southwest. Don't go home remembering this because it's probably wrong, this initial result, but it just kind of illustrates the kind of information you can potentially get out of this. It also says, man, if you're going to be that warm in Greenland, you better be cold in the southern hemisphere. That actually really surprises me because it's not like we have a prior that includes meltwater forcing. We're just using modern observations. But there's something about the system that, yeah, I kind of like that picture. That's a mode that apparently is in the system somehow. And then here's the 8200 year event. the model says, man, if it's going to be that cold, it better be cold just about everywhere. Although it still is warm in Europe because, again, it's unconstrained and it really likes the NAO. Okay? So clearly, you're not really going to just constrain the whole plant with just Greenland. On the other hand, people do that all the time, don't they? They say, here's the Bostic ice core, global mean temperature. This is what you're doing when you do that sort of thing. Okay, last little bit. I said before, I really want to do this with just 018 so the record is totally homogeneous with no calibration, et cetera. It's not quite there yet. I'm going to blow up the right-hand side of the graph to just show you what this looks like. So I'm expanding the scale here, 1850 to 2012. Our results for the high-resolution cores and Nathan's results and the low-resolution cores looks like that. These records only go to 2000. It's always the case that you can't, when you're standing here talking about your paleoclimate data, you never have data that comes up to the present. It's so frustrating, isn't it? It's like, I got to go back and drill more cores. We do have some cores from our European colleagues that go through 2012 that we haven't yet incorporated. I want to incorporate them because I want to see if they do this. This is just the DMI data. This is just temperature observations. I have a feeling this is what they look like. We've seen a lot of evidence, Sarah presented some today, that there's unprecedented warming in Greenland, but I don't think that's a story that's really well known or really that well established. It's established in point locations. This is the kind of methodology, I think, to establish those kinds of results over a large area with high confidence. So look a year from now, maybe hopefully for a publication that says that's true, or actually hopefully it isn't true, but it is true. Okay, thank you. Closing remarks. I think that we're entering a new era where we can do this sort of thing. And it's worth just saying, it's not just because people have gotten smarter or something. It's because people like Greg Haycom, who knew nothing about paleoclimatology 5 years ago, have become interested in our field, and that's cool. These people are wonderful to work with. The collaboration is just so different than what I experienced even 10 years ago. So if you're interested in this, be aware of a couple of things. You probably know about this, but a really critical thing for this sort of effort is high-quality compilations of data. Something that Pages 2K did was it got a lot of data and it threw out anything that wasn't calibrated or couldn't be calibrated against temperature. We need to stop doing that. This methodology will figure that out for you in an objective way. We want all the data, everything that you think is well dated, well measured. Never mind what you think it means. Get it into the databases. That's a big effort that's being made now by the ISO 2K group, by the Linked Earth group. Contribute data to these products. And be on the lookout for our next workshop. The LMR project has had 2 sort of semi-closed workshops. I think this is going to be an open workshop where we're going to actually release code and teach people how to do it and stuff. It's going to be October 2nd to 4th in the Boulder area. I think we're doing an NCAR this year. We should have an announcement out about that soon. And I'll stop there.
Questions?
Sounds like from any of these assimilations you could, where you have delta 18 and temperature, you could pull out precipitation, but wouldn't necessarily be really confident in that, is that right?
Yeah, so precipitation is hard because it's spatially noisy, right? And, without going into too much about all the reasons this isn't going to work. One reason it isn't going to work in some locations, here's a clear example. We're relying completely on the climate model prior, getting the climate in a particular location right. If the ITCZ is 1 degree north of where your proxy is, but should actually be on top of your proxy. I was about to say all bets are off, but it's not actually, it's very clear what will happen. You'll be wrong in 180 degrees. So there's a lot of work to do to kind of deal with those kind of biases. One of the reasons we're using the area interim data, which is actually sort of fixed properly on the globe as climate models tend to be, they'll be slightly off. And yeah, things like temperature don't have such strong gradients, so it's okay, but precip does. Nevertheless, I think that will work over Greenland, which it doesn't have an ITZZ-like feature, right? It's fairly uniform. I think it'll work pretty well. Yeah.
Would you have, from your point of view, an advice to give to paleoclimate community to say focus on the season and on the spatial zone? Like what you showed is like we cannot, or what do you think about this integration of annual temperature for the entire Arctic, for instance?
So yeah, so seasonality is super important, as I think you said earlier today. Somebody did. Most of the proxies are not resolving seasonal variations, but of course some are season specific. Insofar as we're using climate models as a prior, they can be at arbitrarily high resolution. They can be monthly resolution, and we can actually simultaneously use annually resolved O18 to compare with annually resolved O18 simulations, but we could also use proxies that are summer specific, and in the same calculation use only the summer results from the climate model. So the short answer is there are certainly issues to be dealt with in actually doing that calculation and not somehow messing things up, but in principle, we can use all that kind of information simultaneously. So again, any kind of data that reflects the environment should be used. Hopefully you know what it means, or hopefully you have a model that can ultimately be incorporated into the whole system to forward so that we can model your system rather than taking your system and converting it to some variable like temperature. Yeah?
And if I can go further, in terms of, we had a talk about how to talk to policymakers. Would you define or divide the North Hemisphere to the South Hemisphere? Like the very nice example from Raphael Neukom, which showed this difference between North Hemisphere and South Hemisphere, which has a totally different imprint. So shall we provide one temperature curve for the whole globe? Shall we divide per hemisphere? Shall we divide per region? Like you mentioned the PDO.
Haven't we learned that talking to policymakers?
No. How to present data in a better way or how to improve our field?
So one of the reasons for sure that NOAA funded our project is because we sold them the idea that what we were going to do was create a product that is just like the area interim or NSEP, et cetera, reanalysis products, which would allow people to go in and get our paleoclimately constrained results and do whatever they want with them, right? I mean, that's of course not oriented at policymakers, but just fellow scientists want to be able to do that sort of thing. And in general, they can't do it, right? You have to be an expert in the paleoclimate data, you know, et cetera, et cetera. So my answer is I think this is no different than any other kind of climate data. How you present it depends on your audience, et cetera. But the goal here is to have high quality products that the community has produced together and understands really well, and where the uncertainties are really clear, and then we can use those in communication, whether it's between scientists or with students or politicians. Yes, and then Sarah.
I wonder if you wanted to comment on calibration of proxies. We talked a bit
Yeah.
about calibration, and we all frequently go out and measure temperature, measure our proxy, and try to come up with a quantitative version. When in reality, we're in the middle of a huge transient and the system is nowhere near equilibrium. Is it a complete waste of time, or just a half a waste of time, or do you have any thoughts on the efforts that the paleoclimate community has to try to get more quantitative
Well, I think
version?
that, I mean, doing things like that to understand your system are never going to go away, right? Looking at the data saying, here's my proxy, here's the thing I think it measured, how are they related? I think what's new here, it's not really new, but it sort of formalized it here, is that the point of those exercises is not to then use that calibration to just do something, because you're just reducing all this other information, which is outside the calibration, but it's still real information. The idea of those kinds of things ought to be to develop a better understanding of how the system works so that you can model it in a forward sense, so that we can incorporate it formally into this kind of calculation. I mean, I think we've all sort of known this is the goal, but we haven't tended to do it, except for some things which are basically physics, like oxygen 18. But there's no reason in principle that, people have done this, about VS Lite, this program that people use for simulating tree rings. We've used that. It does improve our results statistically. Whether the actual climate result is better is a different question, but those kind of methodologies, I think, are the way to go, and I think we should encourage our students to get really serious about proxy system modeling, which is just the new catchphrase for doing that forward modeling approach. Does that help? Sarah?
If I'm understanding you correctly, how do you handle the fact that there might be multiple distinct solutions that are all dynamically correct, right? When you gave the example, but how do you differentiate? You gave the example like the 82K, when Greenland's that cold, the system wants the NAO to be in place doing something, but that doesn't mean that's the only solution or that that's the best solution for that time, but it's going to pop out.
So the answer to that is that you can, because we're not updating the climate model and having to run it over and over again, we can use an unlimited number of priors. So what we're trying to do actually is develop a sort of database of just things that our code can use as a prior. If your prior...
And that stays in there, it's kind of ingested in the system.
Yeah, I mean, it's sitting in a place on our disk, and we can say, consider that last glacial maximum simulation, because perhaps things happen in the last glacial maximum that never happened in the modern climate. Right. So the way to get that is to have an ensemble of lots of different possibilities. We haven't yet run into the problem that we have unstable results, where there's sort of two equally likely things. I can imagine that happening, but somehow it hasn't yet. Maybe just because the climate system isn't that, it's not actually that weird. I mean, a good friend of mine, colleague at UW Jared Rowe, likes to repeat to everyone who will listen that the first thing you should do when thinking about paleoclimate is just look at winter and summer. The system changes a lot between winter and summer. And you can probably capture a huge amount of what's going on throughout the quaternary, at least, just by doing that. So one thing I've played with a bit is telling the assimilation code that seasonal data is annual data. So it will consider an annual average that it actually looks like winter. In general, that has completely failed. That's the idea. Yeah. The results are model dependent to the extent that the data are not a strong constraint. So again, it's kind of all about the relative uncertainties in the prior, which are given by a combination of declaring what they are and using a large ensemble of priors, and the declared uncertainties in the data. If your data is perfect and you tell it is perfect, then the result will be the data and something in between, right? So yes, it's model dependent, but you can, the better the data, the better the data are, and the better you understand them, the less you're dependent on the model.
One last question?
Yeah, so I'm actually adding on to that point you just made. In my experience, there's relatively low sensitivity to what the prior is, but really the sensitivity depends on the error covariance associated with that.
Yes.
And assigning that error covariance to the state prior isn't always trivial. So can you talk a little bit about how you go about quantitatively?
So I actually can't answer that question because dealing with the error in the prior is not something I personally have tackled. If Greg were here, he could give you a long answer to this. What I have tackled is the similar problem, which is the error covariance in the data.
Right.
And that actually, I think that's of particular interest to the people that produce data, because we talk about, maybe we should drill another core right next to the one we just drilled. We very infrequently actually do this. I've really come to understand how incredibly important that is, because that is the way you actually answer the question, what is my error, and how do I apply it? Although even then it's tricky, because that only tells you something about the local error. It doesn't necessarily scale properly to the grid box.
So is normally like an instrument precision some sort of error that you would assign to the data itself?
That's the default, but the errors have to be much bigger than that, because what you really need is the representativeness error, right? Like, does that core or tree ring represent the grid box size that you're trying to use? There's a rich literature in the weather forecasting world about sort of formal ways to estimate what your error must be, even if you don't know it, and we're trying to apply that approach, but I have to admit, that's like way above my head at the moment, above my pay grade. I mean, I'm doing it, but I don't understand.
All right.
Thank you.
Let's call it there. We can always count on Eric to be moving our field forward. So thanks for such a stimulating talk. The token I have for, so the best climate scientists are often the ones subpoenaed. So when you're subpoenaed, here's a fancy notebook leather holder for